Okay, so 362 if you have the book. So this is our last lesson on thermal physics. So we'll start off with Boyle's law. Have you heard of this guy before, Boyle? Yes, who's heard of Boyle's law before? Yeah?
But not Boyle's law.
Let's have a look. Okay, Boyle's law.
Are we going to experiment from this one?
In DIT? Don't think so. What did I say we do? Newton's second law, Ohm's law, specific heat capacity, and wavelength of sodium light. Okay, Boyle's law. Boyle's law basically says pressure is proportional to 1 over the volume, and that's at constant temperature. Okay. So I'll give you an example. Here's a very simple example. Let's say the volume here is 1 meter cubed, and let's say the pressure is 10 pascals. If I half the volume to now a half meter cubed, what happens to the pressure? It will, no, double pressure, 20 pascals.
Yeah, okay.
This is essentially Boyle's law. That pressure is inversely proportional to volume. So if you half the volume, you double the pressure. And what would happen if I double the pressure?
Half the volume.
Did I just say the same thing backwards?
Yeah.
Sorry, if you half the volume, you double the pressure. And if you half the pressure,
double the volume.
you double the volume.
Why?
What do you mean why? Why is it like this?
What happens when you have more pressure?
Do you see this symbol here? Maybe you haven't seen it in chemistry. This symbol. Do you know what it means?
No.
Oh. This symbol means proportional. It means, the meaning is this, okay? X proportional Y, that means...
If this is increasing, that will increase.
Yes, but more precisely, if X is doubled, then Y will double also. Okay, that's the meaning of this one, Jing Dong. And if I wrote this, it means if X is, sorry, let's say X of course, if X is doubled, then it means Y will be halved.
Mr. Stephen, constant, that's theta, right?
Constant temperature, yes.
We have to memorize the definition of Boyle's.
Oh, definitely. Okay. Now, that's Boyle's law. Another way to state Boyle's law is PV is equal to a constant. So that's the second way to state Boyle's law. You can state it like this, or you can state it like this. First way to state it, second way to state it.
Can you tell me what's constant again, please? Constant. What's the?
Not changing.
You mean theta?
No, it just means it's some number you don't know that's not changing.
Okay.
Okay. Now I want to check if this constant is, yes it is. Okay. So, you might say now, PV equals a constant. What is this constant here? Well, here it is here. Now, you have to tell me if you've seen this in chemistry before. PV equals RT.
Yeah, but
T is temperature now.
yeah, nRT we take.
Or NRT.
Yeah, that's
Yeah.
n for the moles, numbers of the mole.
Okay, use it that way too.
And it's ideal gas constant.
Yes.
8.3
Now-
something is it?
6.02 I'm seeing here.
This R is
Oh, sorry, sorry.
0.413.
8.31, yeah. Huh?
It's not, the R is not 0.413.
No, no, no. The OR here, I'll give you the value of the OR. It's called 8.3, or its value is 8.31
Oh.
joules per mole Kelvin is the unit. This is called the ideal gas law. It doesn't work for every gas, but it works pretty well for a lot of gases.
What kind of gas?
You're talking just something like maybe air in this room,
Mhm.
something like this.
Okay, what's P and what's V?
Yeah.
V.
P is pressure,
Okay, what's the value?
V is volume,
No.
R is this constant, and T is temperature in kelvins.
Yeah, but in chemistry we have a specific value of P. So the same thing in here?
Yeah, well, I'll do an example now in a minute.
It's in room temperature, I think you're saying.
No,
No, no.
temperature, I'm talking about pressure.
Yeah, it's given to you. I mean, you could work it out if you knew the other three or whatever.
Yeah.
I'll give you an example. Let's see. Example, so.
What's big one?
Oh, I might have to make up an example if I can't find one. I might have to make up an example. Okay. There's a second way to write this formula, which I see is the one I'm more familiar with, and maybe the one you're more familiar with too. So this is one way to state it, and the second way to state it is PV equals N or T. I actually use K here. Yes. Yeah, this is this the one you use in chemistry, isn't it? Yeah, this is the one we use in chemistry. Okay, so what's the difference between the two? Well, I think it-
Mole number.
Yeah, that's it. This one here is using mole number. Whereas the other one here, what are we using now? Yeah, if you look at the bottom of page 364, the value of the constant depends on the mass of the gas. And they basically say that it comes out as 8.31. We can now write for 1 mole, PV equals N or equals RT. So in fact, this is just for 1 mole. 1 mole. And this one here is for N moles. So this one is kind of useless to, well, okay, it's kind of useless to us. I didn't want to say useless, but it is pretty useless for us because we never really have 1 mole of N moles. Okay, let's have a look at this one here. Let's see. I want to pick something that we can imagine, like maybe this room. We could know the pressure, we could know the volume, and we could know the temperature. Yeah, so I guess we could work out how many moles are in this room. So I think the pressure, actually, I might have it on my computer here. Yes.
Really?
The pressure is 102.7 kilopascals. So for example, pressure equals 102 times 10 to the 3 pascals. Now, the volume, we have to estimate this. What do we think the volume is of this room? 1 meter cubes. No, it's much bigger than that. 1, 2, 3, 4, 5, 15, I don't know, 30 meter cubed? Would that be too big?
15, let's say it's 15.
2 and 5.
How big do you think that is? 1, 2, 3, 4, 5, about 6?
Yeah,
4, 24 by maybe 2, 40, I don't know. We'll just say 45 meter cubed.
Mr. Steven, any engineer must figure how much the...
We're trying to get the M. How many moles? Okay, the temperature. What do you think the temperature is in here right now?
More than 273.
Yeah, well, yeah, for sure. What do we think?
19.
Is it as hot as 20? Maybe it is 273. Will we say it's nearly 300 Kelvin?
Yeah.
We'll
No,
just say
125.
300 Kelvin. Yes, that's...
Yeah, 73, like 5% or more.
No, the temperature of the room.
Just for the room.
Yeah, just for the room. PVT, okay. Or we already have, or is 8.31. Okay, what else do we want? We have everything? We can get our N. N equals PV over RT. N equals PV over RT. So if you take out your calculator, there's all my information. So if you can calculate, that'd be 102,000 times 45 all over 8.31 times 300.
It's 1841.15 or
18, 1841.16.
16.
Okay, so we'll just say something like about 2,000 moles in this room. Okay? But what is this room made up of? What were we breathing? Yeah, what gas?
Oxygen.
Oxygen, yeah, but I think a much more bigger gas.
CO2.
It was with CO2, but what would be the biggest gas in this room?
Sound.
CO2, I think.
Come on, no, nitrogen.
Why?
You learned this from elementary school, middle school.
What was this?
We are not breathing. We are not breathing. I'm not breathing. We are not breathing. I'm not.
We're breathing nitrogen and oxygen.
Just oxygen.
Well, we're breathing just oxygen, but the air in the room is nitrogen and oxygen. Yes? So do you have your, does anybody have their chemistry book today?
Yeah.
Yes, can you look up the periodic table?
Oh, I have chemistry, no.
Okay. Well, does anybody have a copy of the periodic table? Oh, great. Now let's look up nitrogen. Well, you look it up. Nitrogen, N.
14.
14.
Oh, very good.
Good maths.
Is it 14?
Mass number.
Yeah. Oh, very good, very good. Okay, so I know it's oxygen and nitrogen. Sorry, and what's oxygen?
You want the MR? 16.
16.
Okay, so oxygen is 16 and nitrogen is
14.
30.
14. Okay.
Altogether gonna be 30.
Now, do you remember how you how this works?
Yeah.
Do you remember how? No, when we're using the L, remember? You say in 16 grams of oxygen there are L atoms, and then in 14 grams of nitrogen there is 1 L also. And what was the value for L? It was 6.02 times 10 to the 24?
23.
23 or 24?
23.
23? Okay. Now, I roughly think it's 3/4 this one and 1/4 this one. Okay? So, for example, if I had, let's say, let's make it nice and easy. If I had oxygen, nitrogen, 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 this one would be 16, 14, 14, 14. So what's the total here? 30, 42, 58? Is that right?
No.
No, 32.
72 actually.
Oh,
No,
James.
58, right?
10, 20, 30, 42, 52, 58, yeah?
Yes, you're right.
58 grams, that will equal 4L. 58 grams. Okay, which will equal
Divide by 4.
4 times, what do we say, 6.02 times 10, what's it, 10 to the
23.
33.
23. Okay. Now, how many moles do I have? 2,000.
2000. Yeah, okay.
Yes? So, how many of these will I have?
The total you mean?
Yeah, what will I multiply this by?
I think you will divide the moles by this number.
Well, 58 grams equals this. But this represents 4L, 4 moles, right? This is for 4 moles. So if I wanted for 2,000 moles, what do I do?
2000 multiplied 6.
Multiply by 500.
Yeah.
So if I multiply this by 500, can you calculate that, please?
Divide 500.
Because this is for 4 moles, and I want 2,000 moles.
Okay.
Times 2, sorry.
It's 29,000
29,000
grams.
grams.
Yeah.
So that equals 29
Kilograms.
kilograms. So the air in this room, roughly 30 kilograms. Roughly. Very rough, okay, very rough.
Depends.
Which part?
From the first, from the beginning.
From the beginning. Okay. From the beginning to here.
Yeah. No, more. Yeah. From there, the first line.
Here.
How you got coils around?
Well, this is just from my memory of middle school. I think the air is this right? The air is 3/4 nitrogen, 1/4 oxygen? Is that about right?
72
It's gonna be something roughly like this.
21
Yeah. I mean, we're only doing this roughly, you know, not precisely, roughly. Are you checking it, Jing Dong?
Yes, I'm checking now.
What's wrong, Ted?
Nothing.
Are you sure?
It's mainly made of 78% of
78%.
nitrogen.
Yeah, and how much oxygen?
21%.
Okay, so here, I said about 1/4, 3/4.
That's right.
Roughly.
Okay. Then
Okay. So here, this is 4 moles.
Oxygen and nitrogen, they are 4 moles.
I put 4, because I'm saying quarter,
Oh yeah.
I put them as 4 to make it easier to calculate. So for every 1 oxygen, there are 3 nitrogen.
Mm.
So in total here, 58 grams is for 4 L moles. Oh, sorry. It's for 4 moles. So this is how many. Yeah, I don't actually need this here. You don't have to use this. So 4 moles is 58 grams, but we want 2,000. So I just multiply by 500.
Why is 500? That's what.
Well, how do you make 4 become a 2000? You multiply by 500.
You mean 500 multiplied 2000?
No, 500 multiply 4.
Gonna be 2000.
Yes.
Okay.
So it gives me this. Which gives me this.
When you multiply 58 with 500.
Is this okay, Ted?
Yes.
Are you sure? You seem a little unsure. No? Does the answer seem right? Does 30 kg seem like the right answer for this room?
Yeah.
I guess
why,
so.
Why we didn't multiply 2000 multiplied 58 divided by 4?
No, why would you do that? Oh. No. Okay, you could do 58 divided by 4 multiplied 2000. Is that what you said? It's the same answer. Yes.
What does the 30 kg mean? It means how heavy the
Yeah.
bag is.
Yeah, it means if you took all this air, put it in like a balloon or something, and put it on a weighing scales,
It will be 30
it'd be 30 kg, yeah. Now, look, it makes sense, okay? It should be less than, you know, how heavy we are. Because if this was really, really big, what would happen to us if this was really big? We'd all start to float. Okay? Like if you think about it here, air, water. Okay, this volume equals this volume. Okay? Will this mass equal this mass? No. So will this density equal this density?
No.
No. Which is the bigger density? The water. Now you float in this, but you don't in this. So my point is the mass should be small, because if it was big, we would start to float.
But the thing is, so if you put a baby here,
No, it's about the baby has smaller volume. It's a density statement. I just tried to infer from the density that the mass would need to be small. But yes, with the baby, the volume's smaller, so it ends up being the same. If you think of last week we did helium. Remember helium?
yeah.
And helium balloons float. The helium floats because the helium is less dense than the air. I think 30 kg seems like the right type of answer we should be getting for this room. 30 kg.
The mass on the air.
The mass of the air. I think 30 kg seems right. Yeah? No idea. No natural intuition about it. I think maybe we should do another example. Okay. Let's see. Do we have see, yeah. Let's do the same thing, but let's do CO2. CO2 instead. CO2. Okay, so I have my box, and let's say the volume equals 1 meter cubed, and let's say the pressure equals again, let's say 100. No, what did I say the pressure was today? 100 kilopascals. Okay. Let's say temperature is 20 Celsius. And then what I do is, this gets hot. Sorry, not Celsius. What should I use here?
Kelvin.
Kelvin. So let's say the temperature is 300 Kelvin and it increases to 310 Kelvin. And I want to know what happens to the pressure. Because the volume will stay the same because it's in a box. So do you think the pressure will go up or go down? It'll go up. Let's calculate it. So PV equals nRT. So 100,000 times 1 equals nR300. And then later, it'll have a different pressure. The N will be the same or different? What do you think? The same. And the R? The same. And this is 310. Now if I divide these, I get 300 over 310 equals 100,000 over P. So the new pressure will equal 31 over 30, because I can cancel them, times 100,000. So that's going to be about 103,000.
Yeah, 103,333.
So I'll just say 103,000. So the pressure now will equal 103 kilopascals.
We could do that without this whole thing. We just multiply the pressure by the last.
Yeah. We could use Boyle's law too, but I want to practice using this formula. So by increasing the temperature by 10 Kelvin, what happened to the pressure? Increased by 3%. 3%.
Can you go up, please?
Yeah.
Yes. Yeah.
The volume is 1 meter cube.
Yeah, I made it easy, just a meter cube.
How do you get 310?
Oh, this is my example. I increased the temperature to 310.
Increase
10 Kelvin.
Oh.
Yeah, and I ask you what happens to the pressure. So the pressure goes up.
Now we have to know the numbers of them.
No. I just want to know the new pressure.
Can you go down, please?
Yes.
Okay. Why is he 300 over 310?
Here?
Yeah.
Oh, this is me before, and this is after, and then I divide both. This divide this, and so this one was before. PV equals nRT, and then this is afterwards. PV equals nRT, and then I divide them. They cancel. Yes?
Oh, you get two from
Two, yes.
Oh.
Yeah. Is that okay? Yeah? Alright,
Stephen,
yes.
there is a math class on Friday. After the
There's no maths class after lunch, but there is a class
For ICT.
after ICT.
Why? Not for us.
No, maybe for everybody, yeah.
Do we have?
Yeah, I'll let you know tomorrow.
You have to let us know. Yeah.
I'll let you know, yeah.
Do we have a new timetable for this week?
No.
Yeah, well, just for Friday because of the exam. I'll put it on the page on Moodle, the tutor page.
For the exam, is there any lessons going on during the exam week? 17th to 21st.
You'll have a maths revision class on the Friday.
No, no. The,
Exam week, next week.
yeah, they're
Yeah.
gonna be classes.
Just one maths class on Friday.
That's it. So
Yeah.
we have to just come to
Exams, yeah.
school exam and
Yes.
then go back.
Okay. Now, we're going to go back to our box here. And we're going to, this is on page 366, we're going to look at the gas as lots of little particles.
Which page?
366. So remember what happens? The particle hits the wall and bounces back.
Mm.
Okay? Now, let's pretend it's a perfect collision. So the momentum before equals, let's say, mu, and then the momentum afterwards will equal minus mu. We'll say the E equals 1. We did E, coefficient of restitution, for when it collides against the wall.
Okay. Ah, you mean the power that's in the wall?
Yeah, like this. So that's the momentum before and that's the momentum afterwards. Now the change in momentum
Yes.
will be,
Minus mu.
well, maybe I'll put the,
The before minus after.
I think I'll put this one as the minus and then this one as the plus. Not that it matters. So it'll be mu minus minus mu, which equals 2 mu. Come on, Mustafa, you can see why.
Yeah.
Okay? Yes?
Yeah.
Right, now, next. Time, distance over speed, distance 2L. Okay. So if you look at your particle, here's the, I'll just look at it here. Are you looking, Ted?
Yes.
Are you sure? So here's the particle and it's mu. Comes in, we'll call this distance L, and then comes back out. We'll call it L. So what's the time for this? Well, if you think back, you can use time is distance over speed. So what's the distance here? 2L. And the speed, we'll just call it V. Okay? So if I go down here, I can say the change in momentum over the time, that will equal 2mu all over time, we said, where is it? 2L over V. 2L, sorry, what letter am I using? U, not V. Okay. 2 over U. That cancels that. So I get mu squared over L. Good. Now, I don't know if you remember me showing this earlier, but force is the change in momentum over the change in time.
Yeah.
You remember this?
I think the first question. No, was PV equal delta P over delta T.
You might have done something like this. Look, if you don't remember this, I'll do the proof real quick. It's MA equals, that's MV minus MU all over T. But the M's cancel, and I get A equals V minus U over T. But what's V minus U over T? Is A. So the proof is very short. I think, Albert, you were asking me about this before, weren't you? Yeah, so this is okay? Yeah? Okay, so I have now, therefore, force equals mu squared over L.
Oh, it means the distance.
The distance, yeah, yeah. Okay. Now, pressure, do you remember the definition of pressure?
Yeah. Force over area.
Force over area. So that will equal mu squared over L, all over, what's the area here? L squared,
What's okay,
the
the
distance. Okay. So I get pressure equals mu squared over L cubed. But that's only for one particle, right? We have many particles,
N.
so we need to multiply by n. But this here, that's going to be different for each particle, right? So instead we should use the average. You know average?
Yeah.
So I get P equals n m average speed squared over L cubed. Okay. Now, yes, Jingdong.
We managed to use a vector.
Hmm?
We.
I know it's a vector, so for the moment I've just done it as a straight line, but you're right, the next thing now is that it's a vector. So what's going to happen is, if you look at page 366, can you see this picture here?
Yeah.
366 here? You see this one, Albert? Yes. So,
this formula is average pressures.
yeah, well, I'll get to that now in a minute. But if what you were saying, Jingdong, is you're right, that's a vector. So it's not like this. It's more moving like this in 3 dimensions. But they give you a result. They said if this distance here is, I don't know, W, and then this distance here is X, and then this distance here is Y, and then this distance up here is Z, you have W squared equals X squared plus Y squared plus Z squared. It's like, you know Pythagoras, yes? Pythagoras? X, Y, Z.
Yeah.
It's the same, but in 3 dimensions, 3D. So you get this one. Is that, have you seen this before? Maybe not. Well, Pythagoras works in 3 dimensions also. Okay. Now, what will happen? The particles moving like this, all different directions. So on average, x squared will equal y squared will equal z squared. Why is that? If this is speed,
We're gonna be same distance.
yeah, if the particles moving this way, all different directions, okay? And if no direction is preferred, do you know the word preferred? Ted, what does the word preferred mean? No, my word, prefer. Yeah.
P-R-O-F-E-R.
P-R-E-F-E-R.
You mean in normal English? Or
Yeah, normal English. If I
Make-
prefer something.
make something better than if you.
Yeah,
you
close.
Want something more than.
Yeah, you want something more than the other. Do you know prefer?
Yes.
It means I like it more than something else. I prefer it.
I prefer chocolate and coffee.
You prefer chocolate and coffee. Yes, like this. So these must be equal because the particle must not prefer. Because suppose that it preferred Z, what would that mean? That all the particles were going up. Do you understand?
So that means
Do you see it again?
Yeah. Suppose Z was bigger than these, right? That would mean all the particles would be going up more.
So that means item is going up.
Yeah, here, look. Look here. All different directions, yes?
Yeah.
That means you must have this. Because if z squared was more than these, then what would that mean? that they move around, but they're moving more up than any other directions.
The up in the direction of up is z.
Yes.
Oh, I know.
Is okay? So anyways, you get the result now that v squared equals vx squared plus vy squared plus vz squared. But I said these are equal. So I get v squared equals 3 vx squared. Okay? Is that okay? So now I need to put that back into my formula. Where's my formula gone? Here it is. P equals nmv squared over L cubed. P equals, what did I say it was? Where's it gone? nmv squared over L cubed. V squared over L cubed. Okay. Now, this here, L cubed, what does L cubed equal? That's volume, not this V, a big V, okay? So I can say PV equals V squared. But this part isn't right, because as Jing Dong said, this is for one dimension. But how many do we have? 3. So we get PV equals 1 over 3 n m v squared. That's for 3 dimension.
And big M is the number.
The number of particles, yes. So look, this is just the proof. The proof is really long and really painful, I think. Yes. From this one here.
So we will remember that proof.
No. I just want to teach you so you can feel smarter.
Is this important?
But it's written here PV equal 1 over 3 nmc2.
Yeah, they just use C instead of V because I don't want to confuse. This V is different to this V. That's the reason why.
What are 3D?
3 dimensions, 3D.
Movie.
Like a movie, yeah, 3D movie.
Movie direction doesn't have to be.
Yeah, yeah. You know 3D, yes?
Yeah, I'm just curious about why.
Oh, yeah. 3D. No, because there's no preferred direction. The gas is just moving every different direction.
So that means the thing is not moving.
Yeah, the gas isn't moving in one direction.
But
Yeah.
the item is not moving in the.
We don't take the item moving either. Yeah. Okay, so we have PV equals this. Yes? Okay, let's go back to our example with the room. So what did we say P equals? I got it. What, can you check your notes?
Equal 103.333.8.
No, with the air, with the room. Go back to the room now.
The previous
Yeah, the first one I did.
is 330 kg.
What is it?
103
Kilopascals, yeah? Okay, and what did we say the V was? 45? Yes? What else did we have? The T, what did we say the T was? 300?
Why is V for so high?
No, I'm going back to the question I gave you.
Yeah.
Okay. What else did I give you? Was that it? PVT. Oh, and we know the OR, yeah. What was the OR is 8.31.
And this all formula for the room.
I'm going to do the room again.
R is a constant.
Constant, yeah, constant. Okay. So I know the P, yes? I know the V, yes? I also now know the M. What was the M? M equals 45 kg. Yes? Okay. Now, do I know the N? Well, how many? I think I said 2,000 moles, didn't I?
Yeah.
No,
No, what?
oh, it was 500 times 4 moles.
And I think it's 30 kilograms. Isn't it?
What was? Oh, sorry, 30 was it? No, 29. Yeah, 29. The N is 400 times 4 moles, which is 500 times, what's it, 6 point,
0 to multiplied by 10 over 20.
multiplied by 10 to the 23. Can you calculate this, please?
2012.02.
Yeah, well, this would be 2,000, but times the 6. Yeah, 12.0, 12.12.
1.204 times 1027.
Thank you. That's the N. Okay, let's go to this formula. PV equals 1/3 NMV squared. So PV equals 1/3 NMV. Sorry, I don't want to use this symbol to confuse you. V average squared. Okay. I need to put these numbers in.
What we need from this formula? What
I'm
we
trying to
need?
get the V.
The right and the right. And
This
the
one, this one. Pressure 103 times, what did I say the volume was? 45 equals 1/3 times 1.204. I'm out of space here. I'll go on to times 10 to the 27 times 29 times V squared. So I get now V squared equals 103,000 times 45 times 3 times 3 divided by 1.204 times 10 to the 27 times 29. So, Albert, what's this going to be?
1.995.
Okay, so 2.
2 times 10 power -11. No, that is no square. Yeah, I square root of it.
Thank you. 2 times 10 to the...
Power -11.
Yeah, that seems so small.
Yeah, correct.
Okay, so now what does this represent?
Just in the
The average velocity of the air. So on average, the average speed, so to speak actually, average speed is roughly 2 times 10 to the -11 meters per second. Or that will equal, oh, but that's so small. Isn't it so small?
The grandma's speed.
Huh? Grandma speed, yeah.
Yeah.
Well, I suppose I did do a lot of approximations in this. Although I suppose it's not too bad because the air isn't really moving, is it? Yeah.
There would be wind if it was moving. You don't feel anything.
Yeah, that's true. I suppose if I just left this here, it's not going to move, is it? So yeah, I'm just surprised by how small it is. Okay. Huh? We can Google it. Yeah, I suppose we could actually. So anyways, you have two important formulas. The first one, PV equals N or T. And then the other one is PV equals 1/3
NRT.
M
V squared.
average velocity, average speed squared. So these are important.
And F equals mu squared over L. That just means force.
again?
F equal mu square over L. It just means force.
Pressure is force over area.
And
So what did you just say?
F equal mu square over L.
Yes, that's force. Yeah.
What's NB? Nobody.
No, important note.
Is this part important?
No, I'm just saying these are the two rules which I did in this class which are important. This one is Boyle's and this one, what's this one called? This one's Boyle's
Hard.
and this one's ideal gas law, I suppose. Well, that's also called that one. No, I guess ideal is okay.
IDL.
IDEL. Ideal. It's not a perfect
That's
formula.
I'm handling something.
No, it just means it's roughly true. It's a good approximation.
In chemistry, the name PVNRT is ideal gas law.
Yeah, that's why I did. Well, you see, the confusion part is they're both for ideal gas. So this one isn't. I don't really want to call it ideal.
It's the same.
What did they call it?
Ideal.
Yeah, they call it ideal
And
gas.
Stephen, the P wave, the V just
Volume,
Oh, gas volume.
gas volume. Yes,
Just reverse gas volume.
just gas volume. Yeah.
Okay.
We'll do another example. What will we do? Let's try and think of a real world example. What would be nice to do? Any ideas? No? Does anyone want to do Xingdong, you must give us a real world problem that you would like to do.
You can do like a human with an empty head. Pressure that.
Oh no. Can you think of any real life problems you'd like to try and do?
No.
Or Leslie, you have one. Oh, go ahead.
Well, he has one actually. Do you remember the last lessons?
Okay.
Pregnant.
Do you have anyone?
No. You need some example?
Yeah, can we think of an example
Helium
here?
gas or something.
Hmm?
Balloon or something.
Balloon maybe?
But,
No, I want something to do more with temperature. I'm trying to think of something that gets hot.
Hot air balloon.
Uh, I know. I know what we'll do. We'll try and do something with a car.
Car.
Car, yes.
Okay.
So, you know your car is like this. It has one of these. Okay? And then the gas is inside, and then what happens? The gas gets hot
Yeah.
and expands
I see.
and makes this wheel turn.
Yeah.
So maybe your car has 6 of these.
Yeah.
6 cylinders.
6 cylinders.
Just means column.
Yeah, column, yeah. And now how big are these cylinders? Well, it's going to be like 1 litre, 1.2 litre, isn't it? Isn't that how it works?
140 mm.
Yeah, I'd say like, could we say like 1.2 litre? Would that be right? Because this is how we use it for cars, isn't it? Like, sure, let's make it easy. Let's say it's I know what we'll say. We'll say it's a Toyota Yaris. You know Yaris? Yeah, so these are 1 litres. So 1 litre, how big is 1 litre? That'd be 100 how big is a litre?
1,000 something.
1,000 centimetre cubed. Now, Albert, well no, maybe we don't need this. That's 10 to the 3. Now how many centimetres are in a metre cubed? That's 10 to the 6, isn't it?
Is this a meter cube?
Huh?
Is this a meter?
This here is a metre cubed
Right.
in centimetres.
Yeah.
And yeah, so this means 1 litre equals 10 to the minus 3 meter cubed. Is that right? Yes?
Oh,
Mm,
Yeah.
yeah.
Isn't it?
Yeah, right.
Yeah, is that right?
Yeah, well, yeah.
Okay. So for the car, the V will equal 6 of these. Isn't that right? I don't know. Jing Dong, I'm not very good with cars. Is that what it means? If I have 6 cylinders and it's a 1 litre car, does that mean each cylinder is 1 litre and I have 6 litres?
the way means volume.
Yeah.
The column volume.
The column volume in total, isn't it?
Yes, you can see.
So if I say the car is 1 litre, does that mean this is 1 litre? I always thought so.
But can I say something?
Yeah.
It's not so relevant to this one, but I think there's a problem in this one. It's because 1 liter is 1 decimeter.
Yeah.
And
No, I think this is okay.
you mean please go down please.
Yes.
You mean the volume is the gas out of the motor.
No, I just mean the size of the cylinder. I think it's this. It has to be this. I think so. Anyways, the volume will be this. Because I'll have 6 of them. 1, 2, 3, 4, 5, 6. Now what happens with these? Well, they get full of air, yes?
Yeah.
And then what happens? Then there's a little explosion. And then it gets very hot. Yes?
And the volume.
And then it gets bigger.
Yeah.
So it pushes down. And it makes the wheel turn.
Yeah.
Okay?
I think the fair is in the arm, not down.
Hmm?
The fair is in the arm.
Well, yeah. It's down here, isn't it? Oh, no, sorry, it's up here, isn't it?
Yeah,
Yeah, and it goes, and it pushes down.
yeah.
Okay. So let's start doing some calculating. PV equals N RT. Now I don't know what the pressure is, but I do know the volume. Yes?
Mm.
I do know this. I don't know what this is. And I could calculate this. Yes? I could calculate it. And then what's my other formula? PV equals 1 over 3 NM V squared. Okay, let's get the N first. This N here first. So again, we said it's air. So that would be 1 oxygen and 4 nitrogen. Now, can you remind me please, what are the numbers here?
85. 16, 14, 14, 14.
16 grams,
14.
12 grams,
14.
sorry, 14 grams,
That was aggressive.
14 grams, 14 grams. Okay? Now, the volume, well, will I get the N first or get the M first? I'll get the mass first. So the volume equals 10 to the minus 3 meters cubed. Okay? Alright. Which will I get first? I don't know this one. I don't know this one. I don't know this one. There's a lot I don't know. Do I need more information?
Yeah, the pressure, you want the pressure and the temperature.
Yeah. Well, if I make these equal, if I make these equal, I can cancel the ends. Yeah.
Yeah, but if you
Yeah,
make
we
it
can-
equal,
I think
we
we
will
can-
cancel the PV and the M.
Yeah, go on, Jing Dong.
I think we can get the little m.
We can get the little m.
Yeah.
Can we?
Yes, can I draw
No, tell me. Go ahead. Describe it.
we can find velocity actually.
Little n equals m over. Sorry.
Oh, you're talking about volume over density, isn't it? We know volume. Do we know density though?
Why don't we just equal them so that big n's are going?
Yeah, I'm thinking that. If I make these equal, I can say n or t equals 1 over 3 n m v squared.
So the n will go,
So this will go with this.
but you still don't have the temperature.
But I still don't have the temperature. But I have this.
Yeah, and you don't have the m.
I don't have the m, I don't have the v squared.
Which question is this? Is
I'm
it
making one up. Maybe this is part of the problem. Xingdong,
I think we should add another.
piece of information.
Yes.
Xingdong, how hot does this get?
1003.
Wow, that's very precise. 1003 Kelvin.
Not Kelvin. OC.
just say
Celsius.
Yeah.
Right.
First.
Just say
1003.
Yes. I'm sure.
what?
That's very impressive. Right, can you do 1003 minus 273?
It's
I don't know how you know this, Xingdong. That's very
I-
good.
Because I do this before.
For a car, yeah?
Yeah.
Oh, great, okay. So temperature equals, what's that?
It's 7:30.
730 Kelvin. Okay. So now I know T, so now I can find P.
Yeah.
Alright, let's do P. So, forget this for a moment. Is right, Xingdong? Or did you make a mistake?
And check it again. I remember it's 1,300.
1300.
Yes, I remember it's this temperature.
Okay, it's 1300.
Yeah.
So then it's going to be 1027. Isn't that right?
Yeah.
Okay, great. Alright,
What the hell?
so I have P, which I don't know, times V equals N or T. V is 6 times 10 to the minus 3 equals N times 8.31 times, what did Xingdong say? 1027. Okay, so I can say P over N. So Albert, can you type this in, please?
It's 1422,395.
What is it?
1422,
1422, 395, like this?
Yes.
Okay. Now let's put my information into the other formula. PV equals 1 over 3 NMV squared. PV equals 1 over 3 NMV squared. Okay? P times 6 times 10 to the minus 3 equals 1 over 3 NMV squared. So I get P over N equals 10 to the 3 over 18 MV squared.
I'm sorry, I think it's 2,000 more than 2,000.
2000 now.
Yes.
Oh no, we'll just stick with 1000 now, okay? We can say it's a cold car. 1000's fine.
Okay.
Alright, so we have P over N equals this, and P over N equals this. So I can say this equals 1422395. So Albert, 1422395 over 10 cubed times 18. Can you calculate this, Albert, please?
25603.
What's it?
25603.11.
Okay, now I think you're right, Jing Dong. We can find the m now. So I think we should use, density equals mass over volume. So that means density times volume equals mass. Now we know this. So I get mass equals 6 times 10 to the minus 3. That's times density. And what's the density of air? Do we have it in here?
But there are oxygen and nitrogen.
Oxygen.
Yeah, difference in the density.
Yeah, so we need to mix them together.
And there's a density of error.
Yeah.
Common error.
Yes. Can you check the density of air, please, Jing Dong?
I'm not checking.
It should be something quite small. Air's not that dense. Like maybe. Well, actually, we have it from earlier, don't we? Our room. Our room was 45 meters cubed. And what was the mass? 29 kg.
Yeah,
So the
29.
So the density would equal mass over volume. So it's going to be roughly a half.
0.64.
0.64 kg per meter cubed. Good, okay, so now we have mass equals, Albert please, can you type this in? 0.0038. Good. Alright, now I go back to this volume, I get V squared equals 25603 all over 0.00384. Albert? Thank you.
Oh, it's 666 7448.
666 74
48.9.
48.9.
And the final answer is 2582.1.
After you got square root?
Oh yeah,
Okay. Equals
2582.1.
2582.1. So that equals 2,500 meters per second. Roughly. I guess that seems like a right answer because if you think about it, this cylinder is only this big.
Yes.
So the air must go very, very fast because you need to make the whole car move.
Yes, it's 2.5 L of the motor. It's a very power machine.
Wait, are you telling me, because this will be really cool,
Mm.
you take the L
Yeah.
and you multiply by 2.5 and that equals the V? Is that what you're telling me?
Yes, it's equal total weight.
This is a rule.
Mm.
Is it?
Yeah.
Because we just proved it ourselves. So if my car is 1.2 and if I multiply that by 2.5, that gives me the speed, does it? Are you telling me this is a rule?
No,
Oh,
it's
okay.
not give you the speed.
All right.
It's just to give you how many volume of the gas can be released.
Oh, okay.
When the motor.
It's to do with the release then, is it?
Yeah.
Okay. Good. Now, let's do something really interesting. So here's my cylinder, and I have 6 of them. And here's my particle, and its speed is 2,500 meters per second. How many of these will I have?
And
I'll have n of them. So we need to calculate n now. Now, what's the closest thing I have for n?
P over N.
I have p over n, but I don't know the p. Well, actually, no, hang on, I have the mass. What did I say the mass was? 0.00384. So 3.84 kilograms. Okay. So, grams.
Yeah.
Okay. Now we have to think back. One oxygen. How big was that? 16 grams. And one nitrogen equals 14 grams. But I have 3 of these, so together
58.
4L will equal 58 grams. So Albert, can you do this number divided by this number?
Which number?
3.84 divided by 58.
Black hole.
15.1.
What is it?
15.1.
So about 15 then, is it?
Yeah.
Okay. So I have about 1/15 of this. So my n should be roughly 1/15 times 4L. Okay? So that will equal 1/15 times 4 times 6.02 times 10 to the 23. Okay, Albert again please, or Jingdong?
I missed 4.
1.6
Yeah.
times 1.6 times 10, 23.
Yes?
Mhm.
Great. Okay. And what's my mass? I said is 3.84. So now 3.84 divided by this, what does that equal? 2.4. 10 to the power of 33? 23.
What's the minus?
There is no 10 to the 3.
Did you, Jingdong, can you do 3.84 divided by this? Yeah, it must be minus. Minus 23, yeah? Okay. So if I go back to my cylinder, how many of these particles do I have? N of them. And how much is each one? Now, I know, Jingdong, you said some are oxygen and some are nitrogen. So roughly each one will be this many grams. So roughly each one will be 2.4 times 10 to the minus 26 kg. Okay, let's calculate the energy. That would be a half m v squared. But because I have n of these, it'll be n over 2 times m times v squared, which will equal,
Why is n over 2?
well, I multiply this by n because I have n of them.
Oh, yeah.
Yeah, but actually, yeah, and don't forget there's 6 of these, but I did in total for 6, didn't I? Times 6. Is this for 1 or for 6? Don't remember. This mass, did I say this was for 1 or for 6 of these? Is it?
Do the same. Repeat the same.
I think I maybe said 6. I hope I said 6. Okay. Yes,
I come back late.
that's okay.
My notes
No, that's okay. That's okay.
Sorry.
All right. A half times n. It's 1.6. Where's my n? 1.6 times 10 to the 23. Times m. 2.4 times 10 to the 25. Times v squared, which is 6.6 million about. Okay, Albert.
I'm so lost. What are we doing? Like, why are we doing this now?
I'm getting how much energy is in the cylinders.
1, 2, 6, 7, 2, 0.
1, 2, 6, 7,
2, 0.
2, 0. So the energy is equal to about 1.2 megajoule.
Now we make it multiply 10 power 5.
For what?
The energy.
The energy? What do you mean?
1.2
Yeah?
multiply 10 power 5.
Where's 10 power 5?
No, I mean that's 1, 2, 6, 7,
Yeah.
2, 0.
Yeah, oh, sorry. Well, I wrote M here, megajoules.
Make
Megajoules. Million joules. Did you, is this right? 1, 2, 6. Can you call that again, Albert?
1, 2, 6, 7.
1, 2, 6, 7, 2, 0.
1, 2,
6,
6.
7, 2, 0.
Okay, so actually it's not quite that big. It's more like
Oh, the M means
million, yeah. More like 0.13 megajoules. Yeah. So that's how much energy is in one engine. Does this seem about right? Give me your calculator. Okay, let's see.
It's right.
You know it's right.
Oh, yes, I know.
How heavy is a car, Jing Dong?
How heavy is the
Yeah,
car?
what's the mass of a car?
Not the engine, the total.
No, the total mass of a car. A small car.
A small car.
Yeah.
And about 1.6
1.6.
Tons.
Yeah.
Yes.
Huh?
Yes.
Why 1.6?
I don't know. Ask him. Maybe he worked in the right.
Yeah.
So look here, last part now. That's how much energy. Look here. Hey. That's how much energy is in the engine. Where does this energy go? Into the car. And the car is moving.
Yeah.
So what form does it take? Kinetic energy. Yes?
Yeah.
So that's a half mv squared should equal 0.13 megajoules. So that means V should equal 2 times 130,000 divided by, what did you say, Jing Dong? 1300 kg?
1.6.
1.6?
ton.
How big is a Yaris? A small car, how big? I'd say about this. Small car, yeah?
Let's say
It's in
this.
the car. Yeah, you front seats and back seats.
Yeah, the total
Yeah.
for the car, how heavy? A small car.
Let's say this one.
It's, yes. It's
We say this one? Okay. Albert, calculate please.
14.14.
So, I don't know, roughly 15 meters a second. So that's how fast our car is going. So what did we start off with? We started off with the temperature.
Yeah.
Look, hey, look here. Jing Dong gave me the temperature of what for the engine?
One.
1,200 Kelvin.
Three.
Oh, sorry. 1,300 Kelvin.
Not Kelvin. Sorry.
1,023 27 Kelvin, roughly, will give me 15 meters a second. But then Jing Zhang said, no, it should be 2,000. So this is maybe the car running at
No.
low.
No.
Now, does that look right? Yeah, it does. You know, if I increase the temperature, what will happen here?
Increase.
Decrease. So if the car is going at this speed, the temperature is going to be 1,000 Kelvin.
Mm.
And then if it's 2,000 Kelvin,
Double.
maybe it's double, yeah?
39.2.
Yeah. So if it was 2,000 Kelvin, maybe it's what, 39.2 meters per, what is it? 29. Calculator. So what's that? That's 15 meters a second. So that's per minute. And then per hour. Ah, very good. Okay. So at the start, we said the temperature equals 1023 Kelvin, and that meant that the speed will equal 54 kilometers an hour. And then maybe if we increase this to 2,000, maybe this will be 100 kilometers an hour. Anyways, I realize that was very, very, very long, but the point is those two equations, PV equals nRT and PV equals 1 over 3 nmv squared, only those two, well, we kind of used also mass over volume equals density. These three together, I was able to tell you how fast the car is going if the temperature is 1,000 Kelvin. Or, if I told you the temperature or the speed was 54, I could tell you the temperature was 1,000 Kelvin. I don't know, I think that's cool. We're able to go from temperature to speed. And likewise, we could go from speed to temperature. Okay.
Mr. Stephen.
Yes.
Can you give me the formula when we in the physics test?
Yes.
Ready?
You have formulas in the test, yeah?
I mean, if we can write the formula in paper, in a piece of paper.
No, there's the formulas are at the front page of the physics.
You mean the front page?
Yeah.
And on the exam
So
paper.
we don't need to remember.
No, you have most of the formulas. You don't, the ones you don't have, Ted, is you don't have these formulas.
Oh.
Simple or not one.
Yeah.
And the others, they are in the.
Yeah, like you should have. But I mean, you know this one from chemistry.
No, and I don't mean this one. The first class is the. I mean,
UVATS?
yeah, all of them.
Yeah. Yeah. I think so.
That's for equilibrium. That's
I tell you what, I'll print out a list of the formulas you'll get in the exam so you can see which ones you have. Yes? Okay, I think I should give you some time to practice the questions. I think I actually, yeah, there's one last formula I want to give you. So if I have this here, and its volume is V1, and I make it smaller by V2, and I want to know how much work do I do to do this. Now this formula only works if the pressure is constant. So if the pressure here equals the pressure here, you have a very simple formula for how much work is done. work will equal pressure times the change in the volume. And what's the unit for work? Joules. Okay. So for example, let's take this room. What did we say the pressure was? 103,000 pascals. And what's the volume? 45.
The P is pressure.
Now, let's suppose in this room, I take the ceiling and I push it down. So I push it down so that the new volume will now be 40. So my question is, how much work have I done? Do you understand my question?
Yeah.
So the formula is kind of simple. Work will equal pressure times what? What will I put here?
The V, the first minus.
Tad, what goes here? 5. So that equals 515,000 joules. That's equal to 500,000 joules. So
We have to make as a million joules.
no, you don't have to. So look, please, if I was to take this room and just push it down a little bit, I need a lot of energy to do that. A lot of energy to do that.
Can you go up, please?
Yes. How far now? To here?
Yes, it's here. Go down, please. Yeah, it's here. Work equals PV. V means
Change.
volume.
No, here.
Change in volume.
This here is change in volume,
Mm.
and this here is the pressure.
Mm.
In triangle always means changing something.
Yeah, or small.
Small.
Yeah. The Jingdong, just so you know, the problem with this formula is, look here,
Mm.
the problem is it's only approximately, because this P needs to be constant. But if I close this down, what happens to the pressure?
Increase.
Yeah, so it's a bad formula. It's only approximately.
You mean when you push it down, when you push it down, the pressures are still changed.
Yeah, so it's not a great formula. The only advice I'd say is this needs to be small. And it needs to be, I mean, the pressure, the pressure here should be roughly equal to the pressure here.
Yeah.
So it's not a great formula, but it's useful because it shows you that if I want to make this room smaller, I need to do a lot of work. Actually, bottom please. What's this thing you do? You squeeze it, and then it goes.
Yeah.
Yes. Now, when you squeeze it, the volume gets smaller.
The pressure
The pressure gets bigger. So let's see. Let's try and calculate. Okay. Come on. Right. Volume equals half a litre. So 1 over 2 times 10 to the minus 3 metre cubed. And then I squeeze it. How much do you think I need to squeeze it?
500.
What do you think? V1. What would V2 equal? Come on, give me your idea. What do you think? How much do I need? It's going to be smaller, yeah?
Mm.
How much smaller? Half?
Yeah.
1 over 3 or 4.
1 over 3? 1 over 4? Let's say 1 over 4? Or do you think smaller? 1
1 over 8.
over 8, okay, 1 over 8. So delta V equals
1 over 6.
one,
Actually, what's 1 over 2 mean?
1 over 2.
Oh,
Oh,
yeah.
that's the volume.
Oh,
It's half a litre. Okay, so the change here will be this one minus this one. So that'd be 3 over 8 times 10 to the minus 3. So the work... Now, what's the pressure inside? I don't know. I think it'd be about the same as this room, wouldn't it? Because, like, if I open this,
mm.
the pressure here is the same as here. So then I close it. So I guess it'd be about the same. So 100,000 times 3 over 8 times 10 to the minus 3. So that will equal 1, 2, 3. 3 over 8 times 10 to the 2. 0.3. What will this be? About 3/8 of 100.
75 over 2.
75 over 35 point
Oh, yes.
36 about.
No, 75 over 2.
75 over 2.
Yeah.
Okay, so about 35
Yeah.
joules. About. Now,
No, 37.5 joule.
Jing Dong, it's only approximately anyways.
Okay.
Ted, I'm doing this for you.
Oh.
Put it down. Now, if I squeeze this, I do work. But then what happens? This shoots off.
Yeah.
So the energy here goes into the lid. So let's calculate how fast it goes. So 35 equals a half mv squared.
70.
So 70 over m square root equals v. Now what do you think the mass of this is? Maybe 1 gram? 2 grams?
Yeah.
1 gram?
Yeah, let's say 1 gram.
1 gram?
Easy.
Easier. Alright, please calculate. Oh, sorry. 70 divided by...
It's 264.6.
Ooh, I think that's too big. I don't think it's going 264 meters per second. Do you?
Can go. I mean, at the beginning.
At the beginning, maybe, yeah. I think maybe the mass is too small. Maybe we should say,
Probably will have a very big acceleration, like,
yeah.
I mean, the other acceleration as well.
Let's say 4 grams. Okay, here you go, Albert. You do this for me.
It's gonna be 132.3.
So about 100.
100 and.
Yeah, so something. I guess that answer seems right.
It's very fast.
Yeah, but it slows very quickly, I
Oh,
think.
yeah.
Because it's only this at the beginning. But then as it moves, the air slows it down. So I think the U equals 100 and the V equals 0.
U means beginning speed.
The beginning.
Okay.
I think at the beginning, maybe. Yeah. Do you want to try, Ted? Or maybe you should finish the water first. Or anyone else have an empty bottle?
It's very painful to hit our face.
Yeah, well, it's going 100 meters per second. Does that, you have an empty bottle, do you?
No, I am making it.
No, it's okay. Go on, Ted, finish your water. Let's do it.
It's too much.
Okay. So anyways, my point is here, you can use the formulas from today for lots and lots and lots of practical problems. Lots of practical problems.
Come on, don't go close to the top.
No, don't. You don't have to. It's okay.
No, it's just time.
All right. When's your speaking exam?
Mine is 340 today. Here.
In this room?
Yeah.
Are you happy with all the formulas I did today?
No, but that's before this one you did a big question, so long
Yeah.
was I don't know what's that.
Well, I mean, this is what's going to happen when you go to university. They're always going to do these big problems.
That's why I don't attend less of
What?
Last time we didn't think about a train that for the
that's like what we did.
They use the same thing for the class in that to be.
The train and the car is 100% the same. The hot air pushes and drives the wheel. Yeah. Yeah.
The speaking exam will begin at 3 o'clock.
Will it? I better pack these up. So. All right. So, Xingdong, since you're going to, yeah, please. Can you put the light on, Albert? Since you're going to study this in university, this should be your most favourite chapter.
This is about
Its
material.
name is the kinetic theory and simply.
Kinetic.
Oh yes.
Kinetic theory
Kinetic theory and
of gases, is it?